Hi, so this is part two of my acid-base lectures for this week. And we're going to talk about bases now. We often talk a lot more about acids than we do bases, but we'll focus on bases for a little bit here. So a strong base is anything that generates hydroxide ions completely. So typically what we're looking at are soluble metal hydroxides, so something like lithium hydroxide, sodium hydroxide, where when mixed with water, every one of those units of sodium hydroxide, for example, splits apart into sodium and hydroxide. And so, yeah, any of those soluble metal hydroxides do this, whether it be potassium hydroxide, calcium hydroxide, strontium, barium hydroxide. And so if we know the concentration of that strong base, we can calculate the concentration of hydroxide ions from that, since each one of them dissociates into the ions. And then hydronium can be calculated from that hydroxide ion concentration and the Kw. So let's practice with this a little bit. What are our ion concentrations if we have 2 liters of a solution that has 10 grams of potassium hydroxide? So what we need to do here is figure out the concentration in molarity of the potassium hydroxide. So we first need to convert our mass to moles. So I got 0.178 moles of potassium hydroxide, and that's in 2 liters. So divided by 2 gives us a molarity of 0.089. So if that's our concentration of the potassium hydroxide, and each potassium hydroxide splits and generates one hydroxide, the true concentration of hydroxide in solution is the same. So we have coefficients of 1 here and 1 here, so those concentrations are the same. And therefore, we can also calculate our hydronium ion concentration as 1 divided by that 0.089. So you can work out that math. Ends up being 1.1 times 10 to the minus 13th. Let's talk a little bit about pH. This is, we've used this term before, but we just haven't really delved into the details yet. And pH, it's really a quantification of the hydronium ion concentration. Solution to solution, we get really different values for the concentration of hydronium. From something like, 6 molar, 1 molar, 2 molar, but, kind of molarities that are greater than 1, to really, really tiny concentrations, like 4 times 10 to the minus 14th. And when we have such variation, it's very useful to use logarithms. So the negative log of the hydronium concentration gives us pH, and this picture just is a nice colorful representation of the wide varieties in concentration. So something like battery acid or stomach acid is way down here with a very high concentration of hydronium ions, all the way up here to bleach or drain cleaner, which has a very, very low concentration of hydronium ions. And yeah, that relationship, that pH is the negative log of hydronium ion concentration, that's a definition that you should know. So let's look at some kind of qualities of this scale. So a neutral solution has a balance of hydronium hydroxide, and the concentrations of those 2 ions both have to equal 10 to the minus 7th, and if we take the negative log of that, we get 7. So if we have excess hydronium, more hydronium than 10 to the minus 7th, then we have a pH less than 7, and that would be acidic. Or if we have concentrations that are less than that, we have basic solutions and the pHs are greater than 7. So yeah, the more acidic the solution is, the lower its pH, and with every step in pH, we get a tenfold change in the hydronium and hydroxide concentrations. Just to put in perspective, normal rain versus acid rain. You might think, pH of 4 versus pH of 5, that doesn't really sound like a big difference, but that's 10 times as much acid in acid rain as compared to normal rainfall. So it just makes it easier to kind of deal with this huge variation, this huge range in concentrations. And one thing that's important for calculations that we'll be doing here shortly are that with logarithms, significant figures get a little complicated. But a rule of thumb is that the number of decimal places in the pH value, so in the log value, should be the same as the number of significant figures in the concentration. So regardless of like your placeholders, if you've got 0.0000567 molarity hydronium ion concentrations, you would have then 3 decimal places in the pH representation of that hydronium ion concentration. Because the 5 in the pH or the 6 in the pH, the first number of the pH, that's really almost like a placeholder. That corresponds to how many zeros there are in your concentration. So that doesn't really give you a sense of how accurate the number is. Quick review on just sort of how logarithms work. If we say that y is log of x, we can also sort of rearrange that into exponential form and say that 10 to the x equals y. These are exclusively base 10 logarithms. We don't deal with anything else. And so, yeah, if log of x is y, then we can say that 10 to the x is equal to y. So that means that if pH is negative log of hydronium ion concentration, we can also say that hydronium ion concentration is 10 to the negative pH. So in this first equation here, pH is like the y. This is a base 10 log, and then the x is the hydronium ion concentration. So to solve for hydronium, it's 10 to the negative y, or pH in this case. So you should be able to do some of this math kind of in your head without too much trouble. What are concentrations in a solution that has a pH of 3? So using this form here, if we know the pH is 3, then that means the hydronium ion concentration is just 10 to the negative 3. How about a pH of 8.05? Another thing to keep in mind is that pH and pOH have to add up to 14. And if the pH is 8.05, that means that the pOH is 5.95, and the concentrations of the ions are 10 to the negative 8.05, or 10 to the negative 5.95 for hydroxide. And you can type powers of 10 like this into your calculator. They don't have to be whole numbers to be used as exponents, so on your calculator you can just type 10 to the power of negative 8.05. So yeah, good thing to just keep in the front of your mind is that when you see that little p, it means negative log of. So yeah, like pH is negative log of hydronium ion concentration, and pOH is negative log of hydroxide. We'll also run into pKa and pKb. And these Ka and Kb's are equilibrium constants representing acid dissociation constant, and then also the equilibrium constant for bases, which we haven't really covered yet. Why does the pH scale range from 0 to 14? Is that just random or is it not? Let's work through a quick derivation to show that it's not just random. So we've established that the Kw, and that was in the previous video, this is the equilibrium constant for the dissociation of water. That value is equal to 10 to the minus 14, and it's the product of the hydronium and the hydroxide concentrations. Well, if we take the negative log of both sides of this equation, so the negative log of the product of the ions and the negative log of the 10 to the minus 14th, we can work with this a little bit to sort of derive an equation for pH and pOH. So what we're going to do is split apart this log. So we'll turn this into the negative log of hydronium ion concentration plus the negative log of hydroxide. And then the negative log of 10 to the minus 14th. Well, the log of 10 to the minus 14th is minus 14, and then there's another negative sign there. So those negative signs cancel out, and these negative logs here are just pH and pOH. So from that Kw expression, we get that pH plus pOH equals 14. So yeah, it's not just random that the pH scale is 0 to 14. One more practice here for tonight. And let's look at a base solution of calcium hydroxide. And it says, what is the concentration of hydronium ions? And what's the pH and pOH of this solution? So if we know the solution is 0.008 molar, that's a starting point. last time we looked at a basic solution, we kind of assume the molarity of the solution is the same as the molarity of the hydroxide ions. In this case, we can't do that exactly because calcium hydroxide has two hydroxides in it. And so when it dissolves, every unit of calcium hydroxide, as it splits apart, creates a calcium and two hydroxides. So that means that the equilibrium concentration of the hydroxide is double the 0.008 because there's two hydroxides for every one calcium hydroxide. So once we have that hydroxide concentration, we can kind of approach this problem a couple ways. Well, first way is that the first thing is that we can use the Kw expression to solve for the concentration of hydronium. And when we divide 10 to the 14th, 10 to the negative 14th divided by the 0.016, we get our concentration of hydronium as 6 times 10 to the negative 12th. And then I didn't put on the slide the calculations of pH and pOH, but once we've got those concentrations, the pOH is simply the negative log of the 0.016. The pH is simply the negative log of 6 times 10 to the minus 13th. And just looking at these orders of magnitude here, this is going to give us a fairly low number, something probably between 1 and 2. And then this power of 10 here, 10 to the negative 13th, is going to give us a higher number, somewhere between 13 and 12 and 13, I believe. So yeah, those two, the pH and the pOH, should add up to 14.